Hey everyone, welcome. Welcome to another deep learning lecture. So we're getting really deep into the heart of deep learning now. So before we get started, we'll kind of just talk about the schedule and what's going on. And Arvind and Rohan, you guys said no, so I'll mention the group project meetings real quick. Aside from that, any other announcements, guys? Anything else?
No, Professor.
Okay, great. Let me go ahead and do a screen share here. So I see students are streaming in. Welcome everyone. Hope you're having a good Thursday so far. Hopefully you did not experience any flooding here in Charlotte. We had a whole bunch of rain. Okay, cool. So just a reminder, these are our project check-in meetings. So you are required to have meetings with your TAs and myself. This really is to help all the projects and all the teams be on the same page and keep moving forward. So do schedule your meetings. A few groups have missed a few meetings here and there. And we're trying to decide how to best help you guys stay on track. So if you haven't scheduled a meeting yet this week, please do. So you should be meeting every week with either myself and your TA or just your supervising TA. So make sure you get those meetings scheduled. Aside from that, don't forget that project stage 3 is due Monday at midnight. For some groups, this may be a little faster, especially if you have an industry partner. If you think that it's going to be difficult to reach that goal on Monday, then shoot us an email. Come to your meeting this week, talk to us, and we'll see if it makes sense to extend a deadline. But if there's no reason that if there's no reason for that, then it's due on Monday the 16th, which is the next Monday in your life. So make sure you spend some time on modeling and make sure your group's working on modeling. And again, we've kind of set this up where you've got about, it's about a month between modeling due and your final project due. So we anticipate you probably will do more modeling after this deadline. And some groups aren't doing modeling, right? So, but most groups are, I would say. And this is really to get you going on modeling. We've put this deadline early to make sure you start modeling soon, because what happens in the past is especially on machine learning projects, it can be, how does my audio sound, everyone? I can cut off video if it's okay. Austin says okay. Okay, it might just be you, Dinesh. Maybe try reconnecting and let us know if it stays bad. So what I was getting at is that we put this project deadline a little bit early on purpose, because in machine learning projects, it can be tempting to do all of your training at the end to get your data set just right and get all your data collected and stuff. But it's way better if you train a mediocre model first and get some results, and then you can improve on them over time. So the point of this due date being here is to force you and your group to train something early, so you have a few weeks afterwards to refine performance, to get together your presentation, to do all the stuff you have to do to finish up your project. So, so that is the deadline. It's Monday, so make sure you're working on modeling, make sure you're working on that presentation or on that submission. And then after that, you'll have not that long. I mean, really just 3 or 4 more weeks until the class is over, which is pretty crazy. It will be the holidays before you know it. Okay, so that's just a reminder of our schedule here. Today is going to be another fun lecture getting deep into deep learning. Again, just for a high-level overview, I've kind of already handed you the state-of-the-art tools. So I've said, hey, here's FastAI. Please go use this. Your programming challenge involves using FastAI, so please start looking at that. That will be due on November the 30th at midnight. And now what we're doing is we're really taking a deep dive, right? So we're going to take a deep dive into how do you really get these deep neural networks to train? And FastAI is kind of doing a lot of stuff for you. And that's fine in many cases, but often you'll find yourself having to customize FastAI, to modify things, to write your own code, to fix things. So it's understanding what's happening, what FastAI is really doing for you. It's really valuable. It's going to help you be a stronger deep learning practitioner. So that's what we're doing this lecture and next lecture. And then we have one more really fun deep learning lecture. We're going to talk about GANs. So some of you may have heard of GANs. So GAN is a generative adversarial network. GANs are the technology that are behind deepfakes, for example. So GANs are state-of-the-art ways to make synthetic images, to make fake images. This lecture will be really fun. So this is probably one of my favorite lectures of the year. So we'll do that next Thursday. And then we have a really great guest lecture next Tuesday. That will finish up our deep learning module, and then we're going to be on to 3D modeling, which will be pretty cool, to 3D and key point detection and 3D computer vision. And that's going to be it. We are approaching the end of the class. Okay, I do have one quick announcement I wanted to share. So I would like to recommend a course to you next spring if you're looking for courses to take. And I haven't missed it. I should have asked this before, but Arvind and Rohan, has the deadline passed to register for courses in the spring, or is it still open?
Not yet, Professor. It has
Oh,
to start, I guess.
the deadline has not passed.
No.
Okay, good. I wanted to make sure because
I guess November 30th. November 30th, I guess. That's the
November
date.
30th. Okay, great. So you still have time. Perfect. I wanted to make sure my announcement was was well timed. So some of you may know this professor, Dr. Akela or Shri. So he is teaching a robot motion planning course in the spring. I've heard this class is really, really great, and I just wanted to recommend it to you guys if you're looking for courses to take next year, especially if you're interested in robots, self-driving cars, drones, things like that. So in this class, we cover kind of the basics of how you might build a vision system for your self-driving car or your drone, but it's a whole nother set of mathematics and tools to actually be able to use that vision system to drive your car or to navigate your robot. And it's a really interesting area of mathematics. The math is really cool. You get to learn about things like holonomic constraints and things like that. So Hernan, I don't know. So Hernan is asking if undergrads can take the course. You may be able to if you get special permission. So I would either bug your advisor or you could email Dr. Akela directly. So you might be able to. It's possible if you get permission. So yeah, I've heard this is a really great course. Haven't taken it myself, but I've heard it's quite good. Arvind and Rohan, you guys have not taken this course, I'm guessing.
Yes.
No, Professor.
No, gotcha. So yeah, this is more of a kind of a specialized course, but it is, especially if you're interested in robots, I would have a look at this course. Okay, with that said, let's get into the meat of today's lecture. Okay, so I'll leave my, oh, go ahead.
Yeah, I remember you adding robot motion planning.
I did, yeah. Sri and I are friendly, and he asked me to recommend this class every year, and I've heard good things about it. So I do, yeah. I hope I haven't talked to anyone who took it last year, but I'd like to if I get a chance to and hear how their experience was. I think it's a smaller class, but I've used this part of computer science before in my job, actually, my last job, and I wish I had taken a course on it because it's really interesting, and some of the math was hard to learn when I was on the job, and I wish I had taken a course in it. You have to do this thing called there's this whole set of constraints on the math called these holonomic constraints, and it's really crazy. It's really interesting. But there's a lot to be learned about how to navigate a robot, I would say. Okay, so let's hop into deep learning. Oh, so Sai's taken algorithms and data structures. Yeah, Sri's a really nice guy. I think we're lucky to have him at UNCC. Okay, so what we started to do was I wanted to say, okay, we've seen fast AI. Let's really get under the hood and try to understand how a modern deep neural network works. And we've learned about basic neural networks. We wrote one from scratch in Python, right? We trained it using different optimizers. But deep neural networks, even though in theory and in practice, a deep neural network is just a set of layers, right? Like we've already learned about. There's a bunch of tricks that you need to make them work really well. And these two lectures are all about the tricks and the math and the things that you have to do to be successful in deep learning. And it really is kind of a bag of tricks. So let's get into it. We'll talk about all the different things that are required to do well in deep learning. So I'm going to go ahead and I'll run these live. So let's see here. We already talked about our data a little bit. Okay. We left off here talking about stochastic gradient descent. Stochastic gradient descent. And let me just ask the class real quick. Why do stochastic gradient descent? How is this different than other kinds of gradient descent? And why might we need to do it? Why might we need to do stochastic gradient descent instead of maybe the kinds of gradient descent we did earlier in the class? So I see an answer that it's stochastic or random. Sure. Faster convergence. Yeah, I mean, there's like a really big reason why we can't do. So first of all, what is the opposite of stochastic gradient descent? If it's not stochastic, what do we call it? So batch, yeah, batch gradient descent, right? And what does it mean to do batch gradient descent? How would you explain that to a student of computer vision or deep learning? What is batch gradient? Yeah, so thank you, Abhijit. You put all your data in memory. So every time you compute a gradient, you take it with respect to all your data. You take all your data, compute the gradient, take one step downhill. Now, in practice, a lot of times we just can't do that. Why can we just fundamentally not do batch gradient descent? Why is it impossible for many problems? What happens? So yeah, limited RAM, exactly. And it's actually, in general, we're going to be training on GPUs. So on a computer, on a desktop computer, I can just buy more RAM, or on a laptop, and I can just put it in. I can get like a terabyte of RAM pretty easily. But if we're training on a GPU, then which RAM are we actually talking about? Does anyone know the name? What is GPU RAM called? VRAM, yep. So there's this special RAM in your GPU. Does anyone know like what the max VRAM you can buy off of a very expensive NVIDIA like graphics card is? Like where does it top out? How many gigabytes? Yeah, like 32, 48, something like that. Yeah, I've seen 48, I believe, for like a V100. It's not that much, is my point, right? So pretty quickly you can have more data than you'll ever fit in VRAM. And it's not just fitting your data in VRAM, it's fitting that data as it moves through your whole network, which we'll talk about more. So first of all, you just can't do batch gradient descent. But happily, there's this idea of stochastic gradient descent, which is where we take a random sample of our data set each time. And in practice, it's not that statistical, really. You just take all your data, you shuffle it in random order, and then you kind of walk through it one step at a time. That's really how it works usually in practice. But it turns out doing stochastic gradient descent can actually have other advantages that are actually, in some cases, make it better than batch gradient descent. So let's talk about it a little bit. So last time we left off talking a little bit about some of the concerns. So if you're doing, and the name that gets used often is mini batch. So let me back up a little bit here. So for whatever reason, historically, whenever we do gradient descent on the whole data set at once, or we compute the gradient every single step with respect to all the data, that's called batch gradient descent. And when we do stochastic gradient descent, we have to break up our data into little chunks, right? And a natural name for those chunks might be batches, but the word batch was already used to talk about the whole data set. So we call these mini batches in practice. So whenever you take a little chunk of data to feed to your network to compute a gradient, to take a gradient descent step, that's called a mini batch. And you saw in FastAI, we had the ability to choose the mini batch size. And here are some considerations to take into account when you're picking your mini batch size. So we talked about first, if you use a bigger mini batch size, you will get a better estimate of the gradient. We talked about that. So let's just walk through a few more of these points from Ian Goodfellow's book. And this is I highly recommend this book. This has a lot of good reading in it. Excuse me. So multi-core architectures are usually underutilized by extremely small batches. So this motivates an absolute minimum batch size below which there is no reduction in time. So what he's saying here basically is that if you have too small of a mini batch, you may not really utilize your GPU efficiently. So that's something to pay attention to. Let's see, if all examples in the batch are to be processed in parallel, then the amount of memory scales, this is exactly what we were talking about. So the amount of memory scales with batch size. For many hardware setups, this is a limiting factor. So what this is really saying is just, you can only fit as big of a mini batch as your GPU will support. And if you're training on Colab, for example, and you get an out of memory error, then the first thing you should try is reducing your mini batch size. That should help you avoid out of memory errors. This is an interesting stat. It says some kinds of hardware achieve better runtime with specific sizes. So for GPUs, for example, you usually get more efficiency from powers of 2. So you may have noticed I was picking batch sizes of or mini batch sizes of 16, 32, 8. It's because those powers of 2 are generally, not always, but generally they're going to be more efficient because your data on your GPU is divided into blocks that are usually powers of 2. And then this fact is really, really fun. So this says small batches can offer a regularizing effect. What is regularization? We talked about it briefly in Neural Networks Demystified. What is regularization? What does that mean in the context of machine learning? What does it mean to regularize a network? Any ideas? Prevent overfitting. Thank you. Yep. Good job, Babaji. Good job, Hernan. Great. So regularization is a way to minimize overfitting. And think about it with me for a second, right? So what this is saying is that small mini batches, remember that small mini batches, they don't estimate the gradient as effectively, right? So imagine you're traveling downhill through your complex landscape to find your minimum solution to the problem, the optimization problem. If you take smaller little mini batches, you get more noise. It's like a less accurate estimate of your gradient. but that noise can actually help you find better, more general solutions in some cases. So sometimes we kind of like noise, and having that noisiness that comes from a small mini batch size can actually make your model generalize better, which is pretty interesting, right? So a lot to take into account when you're thinking about your mini batch size. You know, in practice, these are all good things to know, and I encourage you to experiment with them. In practice, I don't change mini batch size too often. I may play with it here and there, but I do want you, since you're just learning about these things, I want you to know all the thinking that can go into setting up a neural network. And notice that this is not like a rigorous theory. This is true of like most machine learning today, right? Well, especially deep learning. Like I can't say, hey, you know, plug in your desired performance into this formula, and the formula will tell you the optimal batch size. So that no one knows how to do that math. It doesn't exist. So these are just heuristics. They're rules of thumb, right? So these are good rules of thumb when you're choosing your mini batch size. Okay. So let's do some of this. Let's do some stochastic gradient descent. So PyTorch has data loaders in it, just like FastAI. And we will be using one of PyTorch's data loaders. And we're going to use that to load up some data. So here is some data loaded up as nice torch tensors. I'm about to visualize it here. So the images are that's our data, of course, and these are our labels. So our labels are stored as tensors, and you can see that the label matches the number in all these cases. Okay, and we're also going to make a validation data set and a validation data loader. And now here's where I really want to kind of pick up where we left off. So the last time that we really got deep into neural networks, we were doing the Neural Networks Demystified module, that series, and we were solving a regression problem. And I specifically chose a regression problem when I made that video because I knew that regression was easier to explain. The math is easier. Classification is actually a little bit trickier. So let's get into that into some detail here. Let me close that. Cool. Okay. So what I want to talk about, so this is I should have asked the class, what does this task feel like here? So we're trying to determine if this number is a 4, if this number is an 8, if this number is a 3. Does that feel like a classification problem or a regression problem? I should have already asked you before I went on to the next section, but what do you think? Yeah, so Sai says classification, Monica says classification, Ravina says classification. Yep, absolutely, yep. Perfect. So yeah, this is a classification problem. We're trying to classify, basically, well, let me ask you, how many different classes would there be in this MNEST data set? 10, right? There's 10 numbers between 0 and 9, so yeah, there are 10. Great. Okay, so that's cool. And now what I really want to start talking about is I want to pick up where we left off with kind of our last neural network that we implemented ourselves. And I want to see kind of how it does, and I want to make some tweaks to make it work well. So if you remember this in.sequential thing, this lets us set up a neural network in PyTorch. And here is a simple 2-layer network that we can use to try to solve our problem, so to solve the MNIST problem. So I'm going to start really, really simple, right? And we'll see if it works, and then we'll kind of add to it. So here is a very simple neural network. How many layers does our neural network have? How many layers does this simple thing have? What do you think? 2. It has 2 layers, right? Here's one layer, here's a second layer, right? And after the first layer, I'm using that sigmoid activation function, just like we did in the Neural Networks Demystified series. Now, notice this. This is kind of interesting, right? So what I'm going to try to do first, just to see if it's possible, I'm going to try to directly predict the label. So, you know, the label, it's just a number, right? It's a number between 0 and 9, right? So why can't I just basically treat this like a regression problem, and just predict one number? Notice my output dimension is 1. Why can't I just directly predict the output? That's what we're going to try first. And I'll just say one more thing. Notice that I have not included a sigmoid activation function after my last layer. You know, so I think when we did the Neural Networks Demystified series, we had a sigmoid on the end like this too, kind of like that. Why have I not done that here? What problem would that create with my strategy? What do you think? Yeah, so thank you, Abhijit. Thank you, Sai. It would squish the value. And what values am I actually trying to predict here? What values am I trying to predict? 0 through 9, right? So a sigmoid would squish it, right? Yep, and we could scale our output data, but for now I'm just gonna leave the sigmoid off. Okay, one other question for you. Why is the dimension of my input 784? Why does that have to be 784? Where does that come from? Any ideas? It's the number of pixels, yep. And as you may know, if you're really good at your powers of 2, I believe the square root of 784 is, I think it's 29, maybe? Well, that's not defined. It was 28, I think. 28? Yeah, 28, cool. Okay, so our images are 28 by 28. So when we unroll them, they become vectors of length 784. One very last question for you. The 64 here, right? What does that tell us about our neural network? What is that configuring in our neural network? It's the number of hidden units, right? Yep, good, Abhijit. Awesome. Yep, perfect. It's the number of hidden units. Could I have done something else? Could I have done like 32, for example? Would that be okay? Yeah, sure, I can do whatever I want, right? Yeah, I could do 100, I could do a million, doesn't matter. Yep, I mean, it will matter, right? But I'm just saying that I have the power to choose. It will impact performance, but 64 is just a guess. All right, cool. And you do have to change both numbers. That is true, Sai. If I change this, I got to change that. Will it throw an error right away, or will it wait until runtime? It doesn't throw it right away. It would complain later, though, I'm pretty sure. Okay, so that is our neural network, and we're going to train this guy. So just like we kind of learned in that PyTorch lecture, we're going to use an SGD, a stochastic gradient descent optimizer. We're going to use a learning rate of 1e to the negative 5. We're going to train for 2 epochs. Here's our loss function. Does anyone recognize that loss function? What loss function is that? Yeah, so lose that m, so there's no mean. It's actually the sum of square errors, but it's the squared error. Yep, great, perfect. If I had done the torch.mean, then it would be mean square error, and it shouldn't make a big difference. So I'm going to train my neural network. So I'll go ahead and start it. Let's go ahead and start training. So here it goes. It's training. And I think it'll go, through 2 epochs. I'm using TQDM to time my loops. And I'm going to plot the loss over time. And let's look at it. Here's my loss function. How does that look to people? Okay, yeah, so Sai says, how do you choose the loss function? So Sai, great question. We are gonna get there in about 15 minutes. I'm actually building to that now, right? So I just chose MSE, Sai, because we've seen, well, I should say just squared error. We've seen squared error before, and in about 15 minutes, we'll find a new loss function, but I wanna make sure we understand why, right? So we're gonna get into loss functions in more detail soon. It's a great question. How do you guys feel about this plot? So this is the loss over time, right? So as we train, our loss goes down, right? How does this plot look to you? Good, bad, medium? If you were training a neural network and this was your loss function, as you trained, how do you feel about it? Hernan says looks fine. Sai says it's stumbling a little bit. The other side says bad, okay, right? Accidentally, okay, yeah. So we have kind of some mixed results. Let's get into the results and see, right? Let's have a closer look. So, so Monica says random. It does go down initially, right? But it doesn't seem like it continues to go down, right? So that to me looks a little suspicious. So here are the predictions from our model. Here they are. I just ran them, right? So let's have a careful look. So remember, y hat is our estimate, right? And these are our inputs. So if the input is 5, y hat is 4.557. If the input is 1, the output is 4.519. So look at these, right? So what do you think? Did we do well or not well? How do you feel about these results? And it is predicting floating point numbers. That's kind of a bummer, right? But we just set it up as a regression problem, right? So in theory, it could do everything. And yeah, so Abhijit has just said something that I'm very happy about. So Abhijit, what did Abhijit say? He said that the neural network has learned to predict not just any number. Look at the number that it's predicting, right? So it's around 4.5, right? And is 4.5 random? No, not really. 4.5 is actually the average. So this neural network has learned to predict the average. This happens all the time. The average is not a bad guess, right? If you're not really learning, but you can just kind of barely guess, then the average will minimize your error because it's right in the middle of all your results. So this happens all the time if you make a mistake or if something isn't set up right. The network has just learned to predict the average, which is kind of interesting, right? So hopefully that makes sense. It didn't do well. And remember, our simple network just said, okay, let's do a 2-layer network and try to directly predict the answer, right? Let's try to directly predict it. So does anyone have a reason why it failed? So it failed to learn, really. I mean, just learn the mean. Any ideas? So Monica's saying that's why we can't use regression for this. So yeah, but let's go deeper, Monica, right? Like you know, regression is, you know, it's just an idea, right? Like what is, you know, it's just a two-layer neural network, and neural networks are supposed to be really smart, right? Why couldn't it learn this, right? So Abhijit, great guess. So Abhijit says there's no bias term. There actually is a bias term. It's wrapped up in that in.linear. So Hernan says the data isn't continuous. So Hernan, you're really getting towards the right answer. You're starting to think about, keep thinking. No linear relationship. So Sai, we had that sigmoid activation function in there. So sorry, Jagadish says no linear relationship. So Jagadish, we have a sigmoid activation function, so we can learn nonlinear relationships. So let's see. Aparajita says it's taking the 0 to 9 as a range of numbers and predicts the average as a general answer. That's what's happening, right? But I'm kind of pushing you guys a little bit, right? Like, is there something weird about how we've set up our loss function and our outputs? Is there something weird about that? Something that, are we kind of asking the network, or what I'm trying to kind of push you guys towards is we've set up this problem in a way that we are penalizing the network in a way that doesn't really make sense. And it forces it makes the network struggle to learn. And this might work with a deeper model, but yeah, so Sean, you're saying we're applying a regression solution to a classification problem. And you're right, Sean, totally. But I want to push you, like, what does that really mean, right? Why can't you do it, right? Let's go deeper. Like, why does this not work? There's something no one has said yet that I'm trying to push you guys towards. So yeah, so Supreet says the loss function does not generalize the difference between 9 and 1. I think you're on the right track. Keep thinking. Think about that loss function. Really think about it, right? So let's go look at it. The loss function is the mean square error. And y and y hat are just numbers, right? So think about the case where like y is like 2 and y hat is like 3, for example, right? So the true label is 2 and the model predicted 3, right? Your error would be 1 squared times a half, right? But it'd be 3 minus 2, right? Now, think about the case where the correct label was like 1 and the model predicted 9, right? So what would our error be then? It'd be actually much larger, right? So Supreet is saying close but still wrong. It's discarded because it's wrong, not considered. So I think you're on the right track, Supreet. Loss is high. Sure. Yeah, so Abhijit, you have said this really, really well. That's great. Awesome. That's what I was kind of trying to push you guys towards. So think about this together with me, guys. So Abhijit has made this point really, really well. So if you think about our loss function, right? So let's just do it, right? So if y equals 9 and y hat equals 1, right? Then the squared error, right? Our loss function value is going to equal, it's like 8 squared, right? And then times a half, right? But I'll just write it like this. So it's 1/2 times, actually we can go ahead and compute it, right? Why not? So it's going to be like 32 or something, right? That's one case. Now, if we have a case where, like, just like Abhijit said, where let's say y is 3 and y hat is 2, right? Then your squared error, your loss term, it's going to be 1 squared, which is 1. It's actually just going to be 0.5. So the network is getting rewarded for predicting a 3 when the answer should be 2 way more, and it's getting really, really penalized if it's supposed to be a 9 and it predicts a 1. So the math word for this, the thing that I would say to describe this, is that we've imposed an ordinality on our prediction. And I kind of talk through it here if you want to read this notebook later. But our loss function is imposing this false sense of ordinality. So ordinality means an ordering, right? In reality, 2 is different than 3 just as much as 3 is different than 9 as far as classifying digits, right? There's no continuum of answers, right? So by using this mean square error, we're pretending like there is, and it provides a very weak signal to the network. Now, you can go try this if you want. Maybe if we used a much deeper network or something, it had more data, I don't know, it might learn. It's possible, right? I can't rule it out, but it's not learning very well, right? This is not a great way to set up our loss function. So that's the idea. I hope that makes sense. So we're imposing this ordinality on our network. We don't want to do that because we want to penalize 2 versus 3 just as much as we do 2 versus 9. Okay, so that's the idea. So to solve this, we're going to use this notion of one-hot encoding. One-hot encoding. So you may have heard of one-hot encoding before. It's a pretty simple idea. Well, let's talk through it now. It won't take you too long to grasp it all, I promise. So I'm going to get an example out of my data loader. I'm going to get an X and a Y. And I'm going to use this torch functional library, and I'm going to call this method called one-hot. That's going to do what's called a one-hot encoding. And I'm going to tell this method how many classes I have. I have 10 classes because it's the numbers 0 through 9. And it's going to do what's called a one-hot encoding. So let's have a look at it. This is the one-hot encoding of this vector y. So I didn't show you the vector y. Maybe I should show you that. That'd probably be helpful. So let's have a look at y. So here's y. And actually, I'm just going to show you the first 5 entries. That's what I'm doing down here. Here's part of y. So the first 5 labels in y in this mini batch are 8, 8, 2, 9, 2. Those are the first labels. So look what one-hot encoding does carefully with me. So if I hand one-hot encoding these first 5 numbers, it comes back with a much bigger matrix. So right, I hand it 5 numbers. Oh, flash flood warning. Okay. If for some reason someone's listening to my lecture driving in your car, then please don't drive into any puddles, even if they seem small, because you might drown. So I assume no one is listening to my lecture while they're driving. That would be kind of dangerous. But if you are, first stop listening to me, and then look out for flash flooding. Okay. So let's see here. So yeah, this is the one-hot encoding of this vector. So notice that these 5 numbers have become a 5 by 10 matrix. And look carefully with me, see if you can see how this works. So here's the first row of the matrix, and there's a 1 in this position, right? And which position is it in? It's in the 0, 1, 2, 3, 4, 5, 6, 7, 8th position, right? So can anyone describe in words what's happening? So what is one-hot encoding doing? What is the relationship between this vector and this matrix? What has one-hot encoding done? How would you describe that in words? It's encoding each number in 1 and 0. So sure, I agree, Ravina, yep. And Abhijit has added a little more detail here. So Abhijit has said the value equals the position. Yeah, so Abhijit's provided some pseudocode. That's nice. So yeah, and Austin has said putting a 1 in the index of the row corresponding to the number. So yeah, Austin, that's a great description. Abhijit, I like your technical description. And yeah, just one little correction that Jagadish has provided. So Austin, it's not the row, it's the column. But other than that, your description was perfect. So we are putting a 1 in the location of the index that corresponds to the value. So if the value is 8, we put a 1 in the 8th location. So that is the idea of one-hot encoding. And let's get into why this might be a good idea, right? So if we one-hot encode our outputs, now all of a sudden we aren't predicting one thing, we're now predicting 10 things. So we're gonna predict like a signal for every class, right? So every class gets its own little output neuron. I hope that makes sense. And the reason that we do that, the reason it's effective, is because it effectively we're like exploding the problem into a higher dimensional problem. So it's like every classification gets to be a dimension in your output space. So you let them be independent. So all of a sudden we can penalize, 2 verse 3 the same we would 2 verse 9. So we're giving every classification, every class, its own output unit. And by doing that, we can get better performance, which you'll see in a minute. So I'm doing one more little thing. I've added this sigmoid back. So notice I've changed the output to be 10 because we have 10 classes. And we're going to one-hot encode our outputs. Why is it appropriate or okay to add this sigmoid back? Why is it okay to add this back? We took it off earlier. Why is it okay now? What do you think? Yeah, so now that we've one-hot encoded, all of our output values, our targets, our Ys, are going to be just 0s and 1s. So having that sigmoid helps the network kind of like, it forces the output to be between 0 and 1, so you're kind of helping the network learn more quickly. And in some cases, maybe learn more effectively and get better performance. Okay, so that is our new neural network. So we're going to do the same thing. We're going to train a model. I'm going to train it a little longer now. I'm going to train it for 25 epochs, a little higher learning rate. I think I experimented a little bit to find that learning rate. For every iteration, I'm going to pass my input through my network. I'm going to one-hot encode the label. And now notice what I'm doing here. So I promised you I would get you a new loss function, but I haven't done it yet. I'm still just using that dumb old squared error, right? And we'll see how it works, right? So I'm still just taking, but I'm doing it with the one hot encoded signals. So now, instead of just taking like 3 minus 2, I'm taking the vector that has a 1 in the third position and subtracting the vector that has a 1 in the second position, taking the difference, squaring those. So it is different, but it still is that mean square error loss function. So let's try it. I'll go ahead and start this training while we're talking. And yeah, we're going to do 25 epochs. It'll take a little bit of time. I'm kind of regretting training for that long now, but I'll go ahead and show you the result here. So I've already run this notebook, I think yesterday. And here's the new curve, right? So here's the new curve. Thoughts on this curve? Do you like it? Do you not like it? Hernan doesn't like that it's jagged, I think. Hernan, do you mean right here, like this point right here? Is that what you mean? Or do you mean like all this noise down here? Like the rest, like the no, okay, yeah, great question. So actually, yeah, Hernan has asked a great question. So first, Sean and Monica say it's better, right? And Monica accidentally said, God, it's better, that's kind of funny. So yeah, so it's definitely better for sure. So Hernan has latched onto something that I really want to talk about. So when you guys were doing your autonomous driving programming challenge, or if you train networks using batch gradient descent, you almost always get a very smooth curve, like really smooth. And actually, I can show you an example really quickly. If I go to github.com/un/CCV/autonomous driving. Yeah, there we go. Cool. So if I go to our autonomous driving module, yeah, look at this. So see this loss function? See how smooth it is? Look how smooth that loss function is, right? Like nice. That's so smooth, right? Now, come back here. Here, look how noisy this is, right? Look at all the noise. And Hernan noticed this, right? So good eye, Hernan. Does anyone know what's changed? Why do we have a noisy loss function? Should I be worried about it, right? What's going on? Why did our gradient get noisy, Abhijit? What did we change? So Abhijit says noisy gradient, true. What did we change that made our gradient noisy? What's different? Perfect. So we're doing many batches, and many batches are because we're doing what kind of gradient descent? We're doing stochastic gradient descent. Good. So because we've broken our data into mini batches, every mini batch has a little bit different estimate of the gradient, so you get this noise. So Hernan, great eye. Get used to this. You'll keep seeing this. It's not a big deal. It's just because we're using stochastic gradient descent. Really, really good question. Okay, so we like this loss function more, right? And let's see how it really does. Let's plot our performance on some real data here. And here we go. So here's some real data. Here's some of our test set. And you got a 6 and a 6, a 3 and a 3, a 6 and a 6, a 1 and a 1. So it's looking pretty good, right? So our labels, or our predictions, seem to match our images. I bet there's going to be a mistake in here somewhere, but I don't see one yet. Wow, you got to even look at that messy 8, right? That's a gross 8. Imagine trying to solve this with like Huff transform and stuff, right? Or with like analytical computer vision. That'd be really hard. Let's see, 7, 4, 9. Are they all correct? Oh, I thought I'd get one wrong. Okay, all right. Let me run this again with a different mini batch. Let's see if I can get one wrong. It shouldn't get everything. Let's see. We'll go back and look at the accuracy. This one is actually very ambiguous. It looks kind of like a 2, kind of like a 7, but I think it's a 7. I would call this a 7. Oh yeah, Abhijit's saying, is there an argmax in there somewhere? That's a great question. I believe so, Abhijit. There must. I'm doing torch.max here. Torch.max includes an argmax basically, so I'm figuring out. So I kind of glossed over this. So our network now predicts 10 numbers, and we'll get into this more, but our network predicts 10 numbers, and we're saying which one of those 10 predictions is the biggest. What's its index? If it has the biggest prediction on the third neuron, it's predicting a 3, for example. So yeah, great question, Abhijit. So yeah, it will get it wrong. So it thinks this is an 8. This is actually a 5. Yeah, so there's some mistakes, right? But it's much better, right? It's doing way better just by doing this one hot encoding trick. And we'll measure our accuracy. We get an accuracy of 91.7%, which is pretty good. Here, accuracy is okay to use because we have a fairly balanced data set. So accuracy is a fine metric. If you're suspicious of accuracy, though, you should be. But here it's okay. All right. So we've made an improvement, but you know, shocker, no one really trains networks this way. So no one does what I've shown you, and let's talk about why. So 91.7% is good, but by MNIST standards, it's actually not good. So we're getting better, but we have a while to go. So yeah, does Torch have an inbuilt function to generate a confusion matrix? So Sai, I don't think so. If someone knows, let me know, but not that I'm aware of. I know FastAI does, but I'm not sure about Torch. I usually don't use just plain Torch usually. Okay, but it's good for lecture because we get to explain kind of the details of how this works. So these two lectures are just using Torch. Okay, so let's get into cost functions. So this is probably one of the more important points of the lecture and probably one of the more important things about deep learning, the loss function or the cost function. So we've been using mean square error or squared error for a while now, and it's really kind of not doing everything we want. There's a better way to do things. And we've seen, at least for some problems, and we've seen that by doing one-hot encoding, we can do better, but we still would maybe like to improve more. So let's have a look at some ideas that could help us improve our loss function. So what I've done here is made a couple of visualizations, and whenever you're training these things or thinking about neural networks, thinking about kind of the loss landscape, kind of the shape of the loss function, really can help you make good design decisions. So that's what I've done here. And I've said, okay, let's just take two cases for a second. Let's assume that we only had 2 classes instead of 10. Let's say that we have like just 0 and 1. So you're trying to predict if an image has a 0 or a 1 in it, for example. If you were doing that with one-hot encoding, you would have just 2 output neurons. This would be like the 0 neuron. This would be like the 1 neuron. And the very last bit of math that you do in this setup is, we have that sigmoid activation function, which is here. So we've written the sigmoid activation function. We're multiplying our weights times our input, which in a lot of books is called H. They call it H in Ian Goodfellow's books. I'm using H here. This is our bias term, and this whole thing is called Z. Now, if we take this output, this y hat, this estimate, and if we pass it into our loss function, the mean square error loss function, and we plot the loss function as a function of our 2 inputs, basically, or our 2 outputs, this is what the loss function looks like. Let me talk through it a little bit more with you. So we have to assume, to make a plot like this, you have to assume what the output is. Let's assume that we have an output of 1, 0. So this would be the case where the true label is 1, excuse me. No, 0, excuse me. So if the image had a handwritten 0 in it, if we one-hot encoded that, then our first output, our first value would have a value of 1, and the rest of the one-hot encoded values would be 0. So this is a one-hot encoding of a value, a ground truth classification label of 0. And the one-hot encoding just goes 1, 0. Because again, I'm assuming that to make this visualization, let's just take a subset of our problem where our only outputs are 0s and 1s. So that's the idea. I hope that makes sense. I've described it up here too, so please come back and read through this if it doesn't quite make sense. So we're taking a subset of our problem. We're just looking at classifying 1s and 0s. And if the true label is 1, 0 like this, after one-hot encoding, we can actually plot the value of our loss function as a function of these 2 outputs. So we have these 2 outputs. I'm calling them Z0 and Z1. It's the output of this neuron and the output of that neuron. So look at this carefully with me here, right? So if Z0 is big, so if Z0 is like 15 or something, right? And this is before it goes through the sigmoid. So this will get squished by the sigmoid. If Z0 is like 10 or 15, and Z1 is very small, like -15, right? That means that our neural network is mostly predicting its output on this neuron. Remember, this neuron corresponds to 0s, and this neuron corresponds to 1s. So if the true label is 1, 0, which is a ground truth value of 0, and our neural network is predicting pretty much the same thing, 1, 0, after we pass it through our sigmoid, which would be this spot in the loss function, then we have a low loss. And it's because these match, basically, right? So the shape of this curve is controlled by this function. We're just plotting the value of this function across different values of y hat. And if it's that case where we have a big value on this neuron over here and a small value on the Z1 neuron, like -15 or something, then we have a small loss function value. I hope that makes sense. So this is literally what the loss function looks like for one example in the 2-dimensional case. Now, over here, we're doing really badly, right? So here, this is basically indicating that our model is predicting a 1, but the true label is a 0. So here we've got a large value for Z1, so a big prediction here, and a small value for Z0. But we know the true value should have a 1 here and a 0 here, so it's like exactly backwards. So you have this plateau here. And then finally, there's this middle range where kind of like you're predicting, in this case, you're predicting a small value for each. So this would have like a value close to 0 for each of these predictions, which is also wrong. It should have a value of 1 for this one. So it's kind of this middle ground where it's half right, and you have the other kind of middle ground over here, where I think they're both 1. So that is what our loss function looks like if we're using mean square error. Okay, now the last thing I'll say before I ask you a question is when you train a neural network, you randomly initialize its weights. And I wish I could show you the plot of the loss function with respect to the weights, which I haven't quite done, but I'm kind of getting there. But there's too many weights, so it's too high dimensional. But here, this is similar. It's to get your brain thinking a little bit about how gradient descent works. And the way gradient descent works is we pick a random value, maybe like here, and our optimizer's job is to go downhill, right? And how does it know which way is downhill? It computes the gradient. And the gradient is just the slope, right? So it's just the slope, in this case, in two-dimensional space. So if we started here, it's going to compute the slope, take a step, compute the slope, take a step, compute the slope, and it's going to take all of these steps, and hopefully it's going to make it down here, right? We hope, right? And remember, this is not with respect to the weight, it's with respect to the output activation. So this is not exactly what the neural network really sees, but it's close enough that it'll serve as a good example for us to think about and to reason about. Okay, so I've said all that. Now, what could be a problem with this loss function? If you were training a model using gradient descent, what kind of issues could happen? What kind of problems could we run into trying to optimize with this surface? What could be some problems with this surface? Any ideas? Yeah, so Abhijit has said it really, really well. He said local minimum. Yep, absolutely. So absolutely, and Hernan said it gets stuck on a plateau, flat minima, absolutely, right? So if you're stuck up here, you may never make it down here, right? So this is not a very ideal shape to optimize on. So maybe the whole premise here, right, is that maybe there is some loss function out there that would give us a better surface. So how do we find it, right? How do we find that? How do we find that better surface? So that's what we're going to talk about next. Okay, and I'd like to share a little quote with you from Ian Goodfellow's book. And this is just a really nice quote that kind of gets you thinking a little bit. So the quote from Goodfellow is, "One recurring theme throughout neural network design is that the gradient of the cost function must be large and predictable enough to serve as a good guide for the learning algorithm. Functions that saturate and become very flat undermine this objective because they make the gradient become very small." So I think that lines up really well with that visual, right? So if your loss function is too flat with respect to your weights, then it's going to be hard to learn, right? So can we find a loss function that makes that better? That's the whole idea. So before we get to this better loss function, and I think we're going to hit the better loss function right at the end of lecture. I think the timing should be good. Before we do that, there's one more thing we need to do because it's really going to help us. Understand this loss function better and understand kind of what the state of the art is. So Monica has asked me to ask Ian Goodfellow for a guest lecture. That would be awesome. Monica, I love that idea. I'm pretty sure Ian Goodfellow will not give me the time of day. He's a senior somebody at Apple or something now, I don't know. But it couldn't hurt. Maybe I'll send him an email. I think he is might be busy. It'd be great. I'll try. I could send him an email. He's a very busy person, I'm guessing, but that would be cool. That'd be super cool to hear a guest lecture from Ian Goodfellow. Okay, let's get into one more thing. So before we do the loss function, we're going to introduce one more thing on the output. So let me ask the class, what output unit are we using right now? What output function are we using on our neurons? What activation function do we have in our output? Thank you, Abhijit. It's a sigmoid. It turns out for classification problems, for single class classification problems like this, where you're trying to predict just one class, there's a better output function to use, and it's called a softmax. So let's talk about the softmax function. This is the formula for the softmax, and we'll get into how that works in a second. But it turns out that when you're doing classification and when there's only one right result, so it's either a 3 or it's not a 3. There's no case of it being like a 3 and a 2. If there's only one right answer, then a softmax generally gets better performance, and we'll show you a little bit about why. A softmax, the way I like to think about it is that it's like a winner-take-all function. So it forces your neural network to pick one answer. So let me show you how that works. So here's the equation. You take the exponential of each value in your vector, and you divide by the sum of those exponentials. And we'll get into that more, and we'll show you how to do it in Python, I think, in a minute. If not, there's some good resources you can look up. But all I really want for you is just to get some intuition. So here's the intuition I'd like you to have. So if this is the output of our neural network before passing it through our activation function, if we apply a softmax, this is what happens. So if we pass 0, 0, 0, we just get an even distribution. So 0.3, 0.3, 0.3. If we pass 1, 1, 2, right, this third activation is still the biggest, but it gets kind of pushed up a little bit more. So it's more than double these. If we go further and we have -1, 2, -1, it's even more dramatic, where this really gets amplified and these really get squished. And I've rounded the answers here. This is actually like 0.9999999 or something, but if we have like 10 in one, this really makes the difference dramatic, right? So it kind of squishes all of your prediction into one neuron is the idea. It's a winner-take-all function, I think is a nice way to describe this. So Supreet has asked a nice question. So Supreet says, softmax does pose the limitation of two numbers in the same image. That's right, Supreet, right. So if you're doing what's called multi-class classification, where it could be like an 8 and a 1 at the same time, or an image could have a dog and a cat, then you do not want to use softmax. So be careful. And by default, FastAI uses softmax. So pay attention to what you're using exactly. If you do want to predict two things at once or multiple things at once, then you want to do a multi-class classification, and if you Google that, you'll find lots of stuff, and FastAI can do that as well. So yeah, but since here we're doing single class, then softmax is going to make life a lot better. So that's what we'll do here for multi-class for single class classification, excuse me. Excuse me, and I put a little disclaimer in here. You should only use it if your labels are mutually exclusive. Okay, so we're going to use this softmax thing. Hopefully that makes sense, but there's one last piece of the puzzle. Oh yeah, so Monica asks a great point. What if there's a tie, like in this case, how do you choose a winner? Usually because of how floating point arithmetic works, Monica, there's almost never a tie. There's always a little bit of a difference. I shouldn't say always though. I'm guessing that it actually kind of depends on this. So most of the time you're going to be using an argmax function, right? So if you have 3 outputs and the outputs are 1, 2, 3, then you know the second or that's the third actually, but this one's the biggest. It starts with 0. But I actually don't know what Python does. Okay, yeah, so I think the default behavior in Python, if there's a tie, it just, or not Python, NumPy, sorry. If there's a tie, it just takes the first one. So kind of not very exciting, right? But that's kind of the default behavior. I'm guessing Torch does the same thing, I'm guessing. Is Torch's argmax function? Yeah, it's like that, cool. So this has to be a tensor, I think. I'm guessing it's going to do the same exact thing, where it just takes the first value. So it's not terribly exciting. Yeah, there you go. So let's prove it to ourselves. Ready? 1, 2, 2. Yep. So yeah, it just takes the first value. Yeah. Not super exciting. All right. So now I want to get into a little bit more mathematics. So how do we choose a better loss function? So we've talked about softmax. We talked about how mean square error kind of sucks because it has these flat regions in the loss function, not great. How do we do better? So the role of mathematics in deep learning is interesting. So, because when you go to study deep learning, you know, like how much math should you worry about, right? Should you go learn a bunch of math, or should you just try experiments, right? And neither approach is really right. I think if you just did experiments all day long, you may do well. If you just did math all day long, you may do okay. But really, some balance between the two is appropriate. And sometimes in research papers, researchers will do a bunch of experiments and then they'll find the math at the end to go publish the paper, but they didn't like do the math first. So just keep that in mind. But this is a case where the math really can provide some guidance. It's not perfect, but we're going to use a mathematical idea called the maximum likelihood estimation, MLE. And this piece of math is a little bit complicated. It uses statistics. I'm not going to quiz you on this, but I want you to know that it's there, and I want you to know that if you would like to have a better, more rigorous understanding of deep neural networks, and if you're considering a PhD or you just want to know more of the math, then this is a great thing to go learn about. And again, Ian Goodfellow's book is a great place to go learn more about it, and there's other resources as well. But I'll just give you the idea in a nutshell. This is an idea from statistics. And just a quote from Ian Goodfellow's book, he says, most modern neural networks are trained using maximum likelihood. So it's a relevant thing to know a little bit about. And here's kind of how it works. Here's the math that we're really looking at. So we set up a mathematical equation like this. So theta, this theta, these are the parameters. So theta is a big vector or matrix that represents all the weights in our neural network. And this is an argmax operation. We'll talk about that in a second. P here is for probability. Does anyone know what this vertical bar means? What does that mean in probability? What does that vertical bar mean? Yeah, given, conditional. Yeah, great, perfect. You guys are ahead of the curve. Great. So the way I read this in English is I say, okay, this is the probability of y. So remember, y is our labels. X is our input, our data. And theta is our parameters. So this is saying the probability of our labels given our input, our data, and our parameters. And the idea here is this says, okay, statistically, we want to find an estimator, a maximum likelihood estimator, that maximizes, we want to find the theta, the values of theta, that maximize the probability of the labels given the input and the weights. If that makes sense to you, great. If not, that's okay. It's not a big deal. But this is kind of where this new cost function is going to come from. So I want to make sure that I'm not just pulling equations out of nowhere. This is where it comes from. So this is a general idea in statistics. We want to find the estimator. We want to find the weights that maximize the probability of the output given the input and the weights. So how do we solve this equation? Like, what do we do with it, right? So we'll take it a little further now. So the first thing we do is we make an assumption, which is kind of how statistics normally works. You have to make some assumptions to make progress. Same thing in machine learning. If we assume that our inputs are IID, which stands for independent and identically distributed, then we can actually rewrite this equation using this big pi thing. What does that big pi symbol mean? So throw it in the chat window. What is that big pi? It's a product, right? So it's a product across multiple values. So what this is really saying is to take the product of the probabilities across all your inputs. So xi, that's every single piece of data. It could be every image in a data set. And what this is saying here is that if you want to find your best estimator in terms of all your data, that's equivalent because basically you're taking all of your data together. So it's like this data and this data and this data and this data. So an and in probability is equivalent to taking the product. If I want to find the probability of flipping heads and heads twice in a row on a coin, I multiply 0.5 times 0.5. So same idea here. I multiply the probability of the label given the input and the parameters across all my examples. So this is really equivalent. And what happens is actually if you go on a computer to compute something like this, if you take the product of a bunch of probabilities, especially for a big data set, you end up with very, very small numbers. And they can become so small that you end up with an underflow problem where you run out of precision, where your numbers are too small to work with. So the answer there, a common workaround, is to instead of taking the likelihood, we take what's called the log likelihood, so it's just the logarithm of this likelihood, of this probability. And as you may know, it's true that the product of logs is equal. You can decompose them into sums basically. So by taking a log, we can turn a product into a sum, which makes our math easier. So solving this equation with a product of probabilities, you'll get the same answer as if you solved a sum of the log of probabilities, and this is much easier to compute. So you may hear things about the log likelihood function. That's where this comes from. So it's the log of of the probabilities, and we're taking the log because we can turn our product into a sum, which makes our numbers easier to work with. So there's a nice quote from Wikipedia that I think explains it really well. It says, for many applications, the natural logarithm of the likelihood function called the log likelihood is more convenient to work with. So that's all we're doing. We're making it convenient to work with. So I've talked about some math. I talked about 3 equations, right? But we're not really at the point of being able to take this and plug it into Python, right? So we're not going to be able to, and the reason is really this, right? Like, what is that probability, right? How do we turn that into code? So we're getting there, I promise. So this part is tricky, I do this, I'm not I don't have a background in mathematics, but I've taken a decent chunk of mathematics classes and things like that. But this math is fairly tricky. And when I was making this lecture, I kind of dug around for a nice explanation. And my favorite explanation actually came from Stack Overflow. And I put a copy here of the explanation, and I also put a link to it. So if you're curious about how this works, please go have a look at that explanation. But this really walks through the math of going from this equation to an equation that we can actually use in Python. So I'm going to skip the math for now, so bear with me. I won't quiz you on this, but if you're curious, please go have a look at it. But if you do this math, you end up with an equation that looks something like this, some kind of equation like this. And notice that our big P is gone, so we don't have that problem with plugging a probability into Python anymore. We now have kind of numbers that we can directly plug in. And really what you end up with is a cost function like this. You get a cost function like this. So this shouldn't look too unfamiliar. We've got a y, and we know that that's our label. We've got a y hat, which is our estimate. We've got a log, we've got a sum, so hopefully none of that looks too scary. And I want to try to give you a little bit of intuition for this loss function. To walk through some math really quickly, but I said, hey, there's this concept in statistics called the maximum likelihood estimator. If we take the log of it, it's easier to work with. We do some math, and then the output is this. We have this new cost function. But does it make any sense, right? So one thing I like about mean square error, so we can hate on it and say that it kind of sucks, but mean square error is really easy to understand, right? So, it's just because we're taking the difference between our predictions and our labels, right? So the more different our labels and predictions are, the bigger the difference, right? So it's intuitive. But if I look at an equation like this, like, oh, a good cost function is the label times the log of the estimate, like why, right? Like, does that really make any sense? So hopefully I can explain this in a way that it makes a little bit of sense and it seems somewhat intuitive. And again, I'm going to rely on just taking our data set down to just 2 classes for a moment. So let's assume we only have 2 classes. And a nice simplifying thing we can do is if there's only 2 outputs and we use a softmax, I actually kind of glossed over this earlier, so notice this with me real quick. When we do a softmax, what do all of our numbers add up to? What do all these numbers add up to in every case? What do you see? They add up to 1, right? So this fits very well with a probabilistic interpretation that these numbers each represent the probability of each class, and if you add them together, you get the total probability of 1. So if I'm only predicting 2 things, right? If I only have 2 classes, then if I predict y0 for the first class, then it's going to be 1 minus y for the second classes. That's the idea. So if I have 2 classes, my summation breaks down just into 2 parts, basically. And I know that since I'm using a softmax, basically, and since I can only have 1 label on each output, that if this term has y and y hat, this term will have 1 minus y, and this term will have 1 minus y hat. So this is finally a function that we can actually plot and have a look at and see if it makes any sense. So let's do that. So I'm going to plot this function. Here is the function written in Python, and here's the plot. And now I really want to take a second and look at this plot. So, and this is also in Ian Goodfellow's book, I believe. So on the x-axis, this is the prediction, right? So our predicted value of y hat, right, between 0 and 1, we're assuming we're doing 1-hot encoding. And this is the ground truth value. We'll just take the blue curve for a second, right, the blue curve. So the blue curve has a ground truth value of 0. So the true label is 0, and this is the prediction. So, and again, we're just plotting the value of this, right? The sum of y times the log of y hat, right? What does that curve look like? So if you look here, right? So when the label is 0, and the prediction is 0, right? What do you see? What is the cost function? What is our cost function value when the label and the prediction is 0, right? And does that make sense? Should our cost function be 0 when our label and our prediction are both 0? How do we feel about that? So Ashish likes it, okay. This is a small value, right? So if your network is doing well, then you should have a small cost function value when it's doing well, right? And here it's doing well because the value of y hat, 0, matches the value of y, right? So it's doing well. As y hat gets bigger, right, our prediction goes further and further away from the true value, and our loss function gets bigger and bigger and bigger and bigger and bigger, right? And it turns out it like explodes when we get to 1, right? So it just like diverges. So our network is going to be penalized very, very heavily if the true answer is 0, but it very confidently predicts 1, basically, right? If it's way off, we get a big penalty. So that's kind of a, something that's a little different than mean square error. On this curve for a second, look at this curve with me, right? So this is if our prediction is between 0 and 1, right? And our true label is 1. So here, if the prediction is 0, but the true label is 1, then we get this huge value, and then it comes down and kind of asymptotically approaches 0. So this is what this new loss function looks like. We haven't given it a name yet, right? We'll give it a name in a second. But it comes from this idea of maximum likelihood estimation. So this is our new cost function. I hope it makes some intuitive sense. And the name that you're going to hear all the time to refer to this loss function is the cross entropy loss. Cross entropy loss. So you'll hear this all the time. It turns out this is not quite the right name for it. It's a really subtle point, but this is a course on computer vision, and we're talking about deep learning, so I want to give you the right information. So in Goodfellow's book, again, he mentions that really this should not be called cross entropy, and I'll just read this quote to you. So he says, many authors use the term cross entropy to identify specifically the negative log likelihood, so remember that log likelihood, of a Bernoulli or softmax distribution. So remember we're using that softmax output. But this is really a misnomer, it's wrong. Any loss consisting of a negative log likelihood is a cross entropy between the empirical distribution of the training set and the distribution defined by the model. So what he means by that is that it depends on what kind of output you're using on your network, and it depends on your assumptions about the data, basically. So for example, the mean square error actually is the cross entropy between a Gaussian distribution, or a 4 Gaussian distribution, excuse me. So what he's really saying here is that I'm going to call this cross entropy all the time, but really what I should be saying, it's the cross entropy, for a softmax distribution, right? So it depends really on the output that you're using. So, but this almost always gets called cross entropy, but just know that it depends exactly on what output you're using and what assumptions you're making about your data. But this is the loss function that we're going to use very, very frequently, and it generally gets called cross entropy. Yeah, so Sai, you're right. So built like all that kind of hand-wavy math I did about the maximum likelihood estimator, that makes assumptions about the underlying probability distributions. And if our assumption is that it's softmax or Bernoulli, which is kind of what we're doing by using that softmax output, then we end up with this cross entropy loss function. But if we actually assumed a Gaussian distribution, then the loss function we would actually end up with, the cross entropy loss function, would be actually our mean square error. So it all depends on the distribution. And by doing this one-hot encoding classification and using softmax, we're basically saying that we were assuming a Bernoulli or a softmax distribution. So there's some kind of subtlety to it. So yeah, Sai is asking if the distribution changes in different scenarios. So yes, absolutely. I encourage you to read the book to learn more about that. But in practice, like, it's not something you really think about too often. The things you really want to know is if you're doing single class classification, multi-class classification, where it could be a dog and a cat, or if you're doing like regression, right? Those are the 3 things you really have to know. And cross entropy is what you're going to use almost always for classification. It's almost always the best loss function. There are other loss functions out there. There's things called like the dice loss function. So there's lots of literature I can point you towards, and the book is good as well. But in this class, like this cross entropy function is, if you're doing any kind of classification, this really is all you need. But I wanted to tell you about kind of how it works and where it comes from, just so you know, and in case you get deeper or as part of your project or part of future research, now you know kind of where to look. So good question. And in practice, we're really going to be using cross entropy. And I should say cross entropy with respect to a softmax distribution. Okay, so that's that. And now let's get into what this looks like. So here what I've done is I've taken our new loss function, our cross entropy loss here, and I've plotted it, right, using the same exact kind of plotting method as before. And what do you notice now, right? How does this loss function look different? What has changed with this loss function? Yeah, there's no plateaus, right? So this is like a nice downhill ski slope, right? You could just ski right down this, right? No problem. So that's the idea, right? And it's time for a poll. So finally, it's been a while since we've had a poll. And this is actually perfect timing. This is a great way to end the lecture. And I think we'll get to the answer, but I definitely want to get to the poll. But let me make sure the question is clear. So I've shown you these two plots, right? So here's the loss function with a mean square error cost function. And here's the loss function with a cross entropy loss function. Now, I must warn you that these inputs, ideally I would like to show you the loss with respect to the weights, but I can't quite do that because we have too many weights, too many dimensions. So here I've just shown it to you with respect to the output units of the last layer, and this is very much related, it's connected by backpropagation to the loss with respect to the weights, but it's not quite the whole story. So keep that in mind as you're thinking about your answer. So here's my question to you. So as you probably guessed, we're about to train another neural network, and the last one we trained achieved an accuracy of like 91% on MNIST. We're about to train one again, and as you're probably guessing, we're going to use cross entropy loss, right? So here's my question to you. When we go train it, will we achieve an overall higher accuracy? Will we actually get a better result? That's A. Or B, will we achieve a similar accuracy, but we're going to find that much more quickly, right? Will we get the same performance roughly, but get there much more quickly? Or are you a skeptic and you think that it's going to be pretty much the same, right? That sure, Stephen, you did a bunch of hand-wavy math. Who cares? Mean square error is still where it's at. I don't think the accuracy will improve. So those are your three answers. So if you guys could throw up the poll, that'd be awesome. And I'll just reiterate the questions one more time. So A, you're saying by changing the loss function, we actually achieve better than 91% accuracy. B says we still hit 91% accuracy, but we get there a lot faster. And C says, no, it's going to be the same 91% accuracy, and it's not going to be any faster. So those are your options. Take a minute. I'm excited to see what the class thinks. Is it a trap? You never know, Sai. It could be a trap. We'll see. Am I trying to trap you? All right, so when you guys are ready, let's close that poll. Let's see what people thought. Okay, so most people said B. You said it's going to be the same, but it will be quicker. So we'll get to 91% but faster. So some of you, the true believers, said, oh, it's going to get better performance, right? And then one person is a skeptic and they said, screw you, it's not going to be any better. Okay, cool. All right, so we got our poll. Thank you guys, that's awesome. So rather than me telling you, let me just show you. So let's get into it. I'm going to make a data loader. Here's our model. It's pretty much the same. I think I was using this many units before. If not, I'll go change it. But I think, oh, we're going to make a baseline actually. Sorry. So yeah, I'm actually going to establish a baseline. And I think I'm just going to show you the results from running this yesterday instead of running it live because we're a little bit short on time. So this is the result from training. I get an accuracy like we saw last time of 91.4%. There it is after 25 epochs. And now here's the cross entropy loss version. So same exact network. I think I don't have the sigmoid on the output. Oh, you know what? There's a reason for that. I'm using cross entropy, and cross entropy has the softmax built into it, basically. That's why. So here's my new fancy loss function, cross entropy. I'm going to train this. Train. And if you look, what accuracy do I end up with? I end up with 94.5, right? And if I look at my plot, here's my plot. So this is accuracy over time, and we'll end with this for the day. I think this is pretty much the end of the lecture. There's just one more fun part. So this is the accuracy as we train, and here's mean square error. So it climbs up, and then it kind of jumps around, and it ends up around 91. Here's cross entropy. So it gets up here way faster after into the first epoch. It's at like 88%, and it actually achieves a better result. So the answer was A. And I know this plot maybe tricked you a little bit because it looks like in this plot that it just is going to end up in the same spot. But remember that this is just respect to the outputs. I can't actually visualize the loss with respect to the weights because it's too high dimensional. And it turns out that in that higher dimensional space, there's actually a better minima. There's a local minima, or maybe global, but probably local minima, that, that cross entropy is able to find that the mean square error could not find. So it literally finds a better answer. Which is pretty cool. So you achieve better accuracy just by changing your loss function. So I hope that makes sense. Just as a little teaser for next time, we're going to basically try to make a deep learning network, or deep neural network. We're just going to start adding layers, and we're going to see how it goes. We're going to see if adding layers, how well we can do on MNIST. That's going to be our next thing. And then we'll hop into the next lecture and discuss, what are some of the ways to get even better on MNIST. And then we'll kind of go through a deeper dive into every layer of a neural network and talk about convolutions and things like that. So it should be a good lecture next time. We'll get even deeper. But I hope that all makes sense. And we talked a bunch about loss functions. So I see a question from Sai. I will answer it right after we finish lecture. Let's go ahead and stop the recording. Thanks everyone for coming. We will see you next week. And I'll take a minute now and talk about Sai's question really quick.